Lesson 9-6, dilations. Dilation. With center C and scale factor K, it is a transformation that maps P onto P prime such that, number one, if P is not on C, then P prime lies on ray CP, and the scale factor K is equal to C to P prime divided by C to P. So what that means is if I'm going to dilate this blue triangle and make it bigger, I draw a line from my center of dilation and I'm going to drag P prime on that line. And then our scale factor is from that point of dilation to the image divided by the point of dilation to the pre-image. Number two, if P is on C, then P is equal to P prime. And we'll talk about that case in a little bit. So down here, we either have an enlargement or a reduction. So PRQ is our pre-image, and the red is our image. So we are obviously getting bigger, so this would be an enlargement. And in the second place, we are with the blue triangle, and we're getting smaller, so this would be a reduction. So an enlargement is a dilation with a scale factor greater than 1. So enlargement means it has to be getting bigger. So that K value we were just talking about comes from C to P prime, which in this case is 5, and C to P, which is 2. So that would be our scale factor, what we would multiply the 2 by to get the 5. In a reduction, our scale factor is going to be smaller. It has to be less than 1 and between 0. So from C to P prime in this case is 3, and from C to P is 6. And always reduce your fraction. So we start at the blue image, and we get bigger by going to the red. Over here we started with the blue, and we got smaller by going to the red. So smaller means it has to be less than 1, bigger means it has to be greater than 1. Thinking back to previous chapters, is a dilation an isometry? So we have to think back to what an isometry is. An isometry is a transformation in which the original figure and its image are congruent. In our own words, all sides and all angles are congruent. So in the first example, we're getting larger, and in the second example, we're getting smaller. Does it look like all side lengths and angle measures are preserved? Yes. And we'll talk more about that later. In a dilation, every image is similar to its pre-image. Have you guys caught my mistake yet? The question above was, is a dilation an isometry? And I said the definition is all sides and angles are congruent. So are you telling me that you just believe that this side and this side are the same length? No, they're not. So this would be a no. The angles look like they would be the same, but the sides are not. So dilations are not isometries. In the second sentence, we learn that they are called similar figures. And similar means corresponding angles are congruent, but the corresponding sides are proportionate. So let's try some examples. Here we have a parallelogram. Notice how the shapes are touching at this point, so that's going to be our center of dilation, point A. So we have to figure out what our scale factor is. So we're looking, for example, from CD and C prime D prime. So CD is 2, C prime D prime is 4. So we have to decide, is this an enlargement or a reduction? So we start with the black image and we go to the blue image. So it looks like we're getting bigger. So is that going to be 2/4 or 4/2? We said this is going to be an enlargement, so it better be 4/2, and to reduce we get 2. So you always want to do your prime first, your image, divided by the length on your pre-image. So if we apply that to this next example, we want E prime H prime divided by E H. So we have 2/8, which reduces to a 1/4. So if we check this out, from blue to black, we are getting bigger. So this is again an enlargement. So did we do that one correctly? No, we didn't. We're going from black to blue, so this is getting smaller. So I would argue that this is actually a reduction, and we were correct with our scale factor. So you always want the primes on top and the pre-image on the bottom. And the center of dilation is going to be point C. So here's our notation for a dilation. It's a capital D, and then 3 would be our scale factor. So for this triangle, we would triple all the side lengths. Down on the bottom, same type of idea, where here would be our scale factor, and X would be the point that we are dilating about. So why don't you try this example on your own. Press pause. So in this shape, our center of dilation is X, because notice they are overlapping. And we want to do our prime length first. So notice that's 8 plus 4, which is 12, divided by the length of our pre-image, which is 4. So our scale factor is 3. So that number is bigger than 1. Our picture is getting bigger, so that's an enlargement. So our rule, we want a capital D, and we are dilating with a scale factor of 3 about point X. Try the second one. Please press pause until you're ready for the answer. So in this problem, the trick is to find the sides that you can count. Otherwise, you have to use distance formula to figure this one out. So our center of dilation is the origin. The scale factor is 2/4. You want to do your prime distance first, or your image distance. So then we have a dilation, which is 1/2 about the origin. Try these next two problems. Hit pause until you're ready for the answer. In the first example, we're looking for some side lengths. So I see a bottom of 2, and then 2, 4, 6 for the other side length. So when we look at that, our 6 divided by 2 gives us 1/3. So our dilation factor, scale factor, is 1/3, and the center of dilation is L for a reduction. Over here, we have the center of H. Our scale factor is 6 divided by 4, which is 3/2, and this would be an enlargement. Let's move our attention to the coordinate plane. If the origin is the center, then what we can do is just multiply our scale factor times our X and our Y coordinate. In other words, multiply the pre-image by the scale factor to get the image. So let's look at this example. What are the coordinates of the vertices? With a dilation of 2, graph the image. So in this case, it might be helpful to write down the coordinates for P, G, and Z. And then what we're going to do is just double. So if I double 2 and I double -1, if I double 0 and double -2, and if I double -2 and I double 1, those are my coordinates. And notice I just had them written in different orders. Draw a dilation of quadrilateral ABCD. Use the origin as the center and use a scale factor of 3. So let's not pay attention to the graph for just a second. Let's work on our coordinates. So we're going to take the 3 and triple every number that we see. 1 times 3, 1 times 3, 3 times 3, 2 times 3, and so on. So those are going to be our new coordinates. And now if we plot them, so go ahead and plot your originals and the dilation. Hit pause if you need more time. Here is our new figure after our dilation. Notice we're using the origin as our center. So if I connect from there, it's 1 unit long, or just from one diagonal long. And if I do to the purple, then I am doing 1, 2, 3 diagonals long. So there's that scale factor of 3 showing up again in terms of the center of dilation. Try this one on your own. Pause the video until you're ready to see the answers. So I'm going to multiply every coordinate by a half. So my blue rectangle turns into the green, so it does get smaller. In terms of the center of dilation, if I draw lines from my center of dilation, notice it goes through my image and my pre-image. And that should happen. So in terms of the distances, the distance with the green divided by the pink would give us that ratio of a half. And that's where all those values are coming from, is because of the distances from the center. But when we're in the coordinate plane, we're just worrying about the coordinate values and multiplying them by k. This concludes the lesson.